So in this video, we're going to talk about Rolle's theorem. So I'm going to let f be continuous on a to b and differentiable on open interval a to b. All right, so this has the same setup as the mean value theorem. All right, Rolle's theorem, same setup as the mean value theorem. Now, I'm going to add to the mean value theorem. Rolle's theorem says assume f of a, the left endpoint output, is equal to f of b, the right endpoint output. Okay, that's the assumption that we're adding to this. So instead of just having some random curve that's continuous, the difference is this left endpoint and that right endpoint have to be equal to each other. Okay, so that's the difference. So f of a is the same as f of b. So we see that there's a line up here because they are equal to each other there. All right? Now, if this is the case, then there exists one number c in AB. Okay, so there's a number c in AB such that, well, guess what? It's not just one number that matches up here. You have at least one number. So I wanted to emphasize that for you. It's not just one potential C. You could have multiple C's, okay? So there could be more than one C, just so you know, all right? So then there exists at least one number C in AB. So that means there's some number between A and B not equal to A, not equal to B, but between those two values, okay, such that what? The derivative evaluated at C is equal to 0, meaning my slope of my tangent line on this curve is a horizontal line. So you can see here for C1, this gives me a horizontal line, and for C2, this gives me another horizontal line here. So Rolle's theorem basically says this: if a curve goes up, then eventually the curve is going to come back down if I know that the endpoints start on the same level. Okay? So if I know that the curve is continuous, if I work my way up, eventually I'm going to have to work my way back down because I know that the endpoints have to be on the same level. That's all it says. What goes up must come down, and vice versa. If it goes down, then eventually it's going to have to go up. Now, it may keep going up and then come back down. Heck, it may just go down and come up, right? So we don't know what happens between. There could be multiple points where we have that turning from going uphill to downhill, right? Or from downhill to uphill back again. There's multiple turnings here. That's why the theorem says at least one number, because it could be 1, could be 2, could be 3, could be a ton, right? But there's at least one, all right? So Rolle's theorem is just a special case of the mean value theorem. So what do I mean by that? The mean value theorem, if you think back to the mean value theorem, what does that say? It says the derivative evaluated at that critical, that C point, okay, that number between A and B, is equal to the slope of the secant line of the endpoints. But the difference is here, you think about what is the slope of the secant line in Rolle's theorem. The Rolle's theorem is literally has a slope equal to 0 for my secant line. So instead of it being equal to this big old thing, that big old thing is just equal to 0 because it has a slope, a secant slope of 0. If f of a equals f of b, then f of a minus f of b, or vice versa, is equal to 0, which 0 over whatever number is equal to 0. Okay? So that's why I set f of c equal to 0 here. That's Rolle's theorem. All right? Now let's prove Rolle's theorem. And the reason I prove Rolle's theorem first is because I use Rolle's theorem to help prove the mean value theorem. So we need to prove Rolle's theorem first, and then we'll prove the mean value theorem. So how do I prove Rolle's theorem? Well, to prove something, we have to start with the assumptions. What are my assumptions here? I let f be continuous on the closed interval and be differentiable on the open interval, okay? So I'm going to assume that it's differentiable on the open interval. Then we get continuous for free if it's differentiable. Now, what else do I assume here? If f of a equals f of b. So that's an assumption too. If this is true, then this follows, right? So my assumptions here are this line and this line. So not only do I have this first part, but I also have f of a equals f of b. Now, this is all I have to work with, and I need to prove somehow that there exists at least one number c between a and b such that the derivative is equal to 0. Okay, so let's do that. To do this, I need to break my functions up into two cases. Two cases, people. So the first case, assume that f is a constant function. What are constant functions? Constant functions look like this. They're just straight lines. So that's like f of x equals 4. So no matter what input of x I spit in, it always puts out a y value of 4. That's a constant function. Kind of boring, right? But that's case 1 is a constant function. So it's constant on a to b. So that makes sense that it would fall into this case because a constant function, f of a would equal f of b, right? We know that to be true if it's just a horizontal line. Now, that is any x value that I plug in, but in this interval a to b, is equal to f of a, which is also equal to f of b, right? Because I just showed you, you got your line here. If I have some f of x, and from a to b, and it's constant, that means no matter what x I plug in, it's always going to be equal to f of a and f of b, right? A constant function, okay? So that's the idea there. For all x in a to b. Now, if that's the case, what do you know the derivative of a constant is? What's the derivative of 4? Well, the derivative of 4 is equal to 0. It has a horizontal line. It's a slope 0. Okay? For every x value in AB. That implies that there is at least one c between a and b, because we're saying all the c's between a and b work, right? So therefore, at least we can pick one. You think about it. If I'm saying from a to b, that every x value that I can think of in here works, right? Every x value I plug in equals f of a, which equals f of b. Then by golly, I can at least pick out one c value that works, right? At least one, obviously, okay? Such that f prime of c is equal to 0, which is exactly what I wanted to prove there. That's case 1, okay? Now, case 2. So I'm breaking it up into two cases. Either I'm a constant function or, guess what? I'm not a constant function. Okay, so now I'm assuming that it's no longer a straight line. So it's like this scenario here. It's not a constant function, all right? So it's not constant on AB. Then what do I know? Well, I know that I can apply the extreme value theorem to this because what? It's continuous on the closed interval a to b, right? And so therefore, I know for a fact that the extreme value theorem guarantees that I have a maximum and a minimum value somewhere on the closed interval a to b. So the extreme value theorem says this is a closed interval on a to b, therefore I have to have some point that's an absolute max and some points that's an absolute min. Now, they may occur at the endpoint, right? But technically, it cannot. Why do we know that it cannot occur at the endpoint for this scenario? Well, what is my assumption? It's not constant. Therefore, at some point it goes down or it goes up, right? It's not a constant. And whenever it goes down or up, all of a sudden, this thing can no longer be a max and a min at the same time, okay? So it's found either at an endpoint, right? Using the Clark way, we find max or mins like either at an endpoint or at critical numbers, right? Where the derivative is equal to 0 or does not exist. So there's some C between A and B, such that those are critical numbers, right, by definition. Now, what do we know? We have assumed that f of A equals f of B, okay? So since f of A equals f of B, and f is not constant, all right, then the max and min cannot both be at endpoints, all right? So what I just explained here, there is no way to have a max and a min at the endpoints. If the function's not constant, then I have a max up here, even though these are mins at the endpoints, but not both max and min. And then this scenario, I have a minimum here, but then my maxes are both the same here. But it's impossible for my max and my min to be the same as the endpoints if the function is not constant. The only way that's true is if I'm dealing with this straight line here, and then that would be case 1 of my proof. Okay, and so I've already proved case 1 part. So I'm moving on to case 2. So what I'm going to do is I'm going to assume without loss of generality. This is a fancy way to say pick one. Okay, it doesn't matter which one you pick, but you need to pick one. So either pick the maximum or the minimum case, and they're proved the same way. So we pick one so that we don't have to redundantly prove the same thing for the minimum. So I'm going to pick, without loss of generality, a maximum of f is not found at the endpoint. So what does that mean? That means at some point our graph, the endpoint, the maximum, is not here, so it has to be somewhere in between, right? That's what we're talking about, that scenario. So if I draw a picture, I'm assuming what? I'm assuming f of A is equal to f of B, and then I'm assuming that there's some maximum that's not at f of A and f of B. So that means I draw a curve like this, and there's a maximum. There's at least one C between A and B where the maximum value is f, and this is given to us directly from the extreme value theorem, okay? So that's my max. Now, thus, what? C must be a critical number of f. Why? Because it's at a maximum, okay? And since f is differentiable, so f is differentiable on AB, then what do we know? The derivative here, well, what's the derivative at the top of the apex here? It must be equal to 0, critical value, right? So that's a direct result from that theorem. And therefore we've finished, okay? So in the next video, I'll show you how to prove the mean value theorem. Pretty easy once we have Rollies Theorem or Rollies Theorem. I've heard that. It's called that before. I call it Rollies Theorem, good old East Texas, right? Okay, so we just proved Rollies Theorem here. Basically, if you know that the endpoints are equal to each other and it goes up, at some point it's going to have to go down. That's all it says.